name is Pranay Nagrani, and I am currently at Purdue University, and I graduated from NITK in 2019. So I'll just give a small talk about what partial differential equations are and the various. I would an open source CFD solver. So I would focus on OpenFOAM because that is something I have worked with pretty extensively. So if at any point anyone has a doubt, please feel free to stop me and ask me over there. That should be totally fine. So to get started with, I have three different sections today. So one is basically just an introduction to what PDEs are, and then I would talk about the discretization methods, and finally I'll move over to what OpenFOAM is, just introduce it, and basically people who want to get started, who want to get a brief introduction to it, this is a pretty good place to start. So yeah, so starting with, so for partial differential equations, it's basically one of the most general form is something that you're seeing on your screen right now. So it's when the dependent variable has multiple independent variables. So over the equation over here, you can see the subscripts t, x, and y. So these are the independent variables, and the dependent variable is u over here. So when you have such multiple independent variables, that is why it's called a partial differential equation, and you don't write d when you write the notation, you write a dou notation. And yeah, so that's the basic what partial differential equation is, and these are pretty important from if you're doing a basic CFD simulation. So coming to how we use partial differential equations in CFD, so to explain you the different partial differential equations, just consider the equation that you see on the screen over here, and whatever I'm talking right now is just applicable for a second order partial differential equation and not for more higher order ones. So we basically group the first derivatives in this term h, and also all the other constants in this term h. We are mainly concerned with three terms over here. So double derivative with respect to x, double derivative with respect to y, and a mixed derivative term over here. So now to determine what type of partial differential equation it is, we basically we find a discriminant that is basically b squared minus 4ac, and depending upon the value of this particular term, we can classify it either as a parabolic equation, elliptical equation, or a hyperbolic equation. Now classifying is one thing, but why this classification is important is that different types of PDEs are solved differently in CFD. So I'll explain, this will become more clearer in the next slide. But if I know that I'm solving a parabolic equation before starting my CFD analysis, I would know, okay, so this is a parabolic equation, these are the numerical schemes that work the best for parabolic equation and can give me a convergent solution pretty quickly. And if I use, say, for example, the numerical scheme that works well for elliptical equation to solve a parabolic equation, I might not get a converged solution, or even if I'm getting a solution, it might not be accurate. So that is why it's pretty important to know what type of PDE you're solving before starting a CFD analysis. So yeah, so just an example of the previous slide. So over here, on the top left, you see that we have just two double derivative, dou squared f by dou x squared and dou squared f by dou y squared. And if you convert it into the form I showed on the previous slide, it basically comes out to be minus 4, the discriminant value, which is less than 0, and hence we classify this as an elliptical equation. And similarly over here on the top right is basically we have one single derivative and other one as the double derivative. So all of these terms, single derivative, as I told you, goes into that h term over here, and therefore it's not present in the coefficients at all. So we just have one coefficient d over here, and depending upon the value of that, we can calculate the value of the discriminant, and for parabolic equations it will come down to 0. And finally we have the hyperbolic equations, and out of these three classification of equations, hyperbolic equations are one of the most toughest equations to solve. It's mainly because they have a lot of it's basically hyperbolic equations. For example, I would start is if you have any supersonic flows, Mach number greater than 3.0, then all those governing equations come under the classification of hyperbolic equations. And in these equations, we see something known as shock waves. So they are basically a very instantaneous change in any of the fluid property. For example, density might change very rapidly over a very small amount of spatial discretization in your xy plane. So when such a thing happens, it's very difficult to solve such a class of CFD problems, and therefore hyperbolic equations in itself has a separate topic. And on the top, elliptical and the parabolic ones are much more simpler, and there are a lot of CFD analysis already been done on these equations. So now I just wanted to introduce these equations from a CFD application point of view. So for the elliptical one, this is the main equation form. I would like to say this is like the template. So you see any equation of this particular type, it would be an elliptical equation. So some of the examples, so this is known as, before going to the examples, this is known as either a Poisson equation or Laplace equation, and this is what every basic CFD engineer must know about it. And so for example, it's the steady state temperature distribution. So now if you replace u with t, so your x and y are basically your x and y plane. So the equation of the type t xx plus tyy equal to 0 is basically solving for the temperature profile on a 2D plane, and which is an elliptical equation. So you would use all the numerical schemes and the resources which are used to solve elliptical equations to solve the temperature equation in this case. And elliptical equations don't have time derivative. It's always a steady state problem. Coming on to the next one is the parabolic equation. So in the parabolic equation, it always has a time derivative. It's a time dependent equation. So and in CFD, time dependent equations are known as forward marching equations. The reason being, time always goes in a positive direction. We always go from t equal to 0 to t equal to time t. But on the other hand, in space, we can go either x equal to 0 to minus L or x equal to 0 to L. So we can go in both the directions. But when it comes to time, it's always in the forward direction. And that is why these type of equations are known as forward marching. And always remember that the parabolic equation will have a derivative with respect to time. An example of this one is basically if you consider 1D diffusion of heat in a bar, and basically transient diffusion or a steady state diffusion. And coming to the last class, that is the hyperbolic one, one of the most famous examples is a wave equation. And also basically it can also be a supersonic flow equation. So all those type of equations are governed by this particular template of the partial differential equation. And as I said, these are the most difficult problems in CFD, and there are multiple numerical schemes for these problems, each one of them have their own pros and cons. And before using any of them, one must be sure about the different scenarios that they want to simulate for. So this was just a brief introduction about PDEs. And if you go deep into each PDEs, it's basically there's an entire book on each one of them. So therefore, suppose you're solving you're simulating a particular CFD flow problem, and if you know that you have a parabolic equation in your hand, there's an entire book on how to solve these parabolic equations. So coming to discretization methods. So I was told that many of you already know finite difference method, and finite volume method is something you guys don't have much experience with. So I'll first just introduce what finite difference method is, and then I'll jump on to finite volume method. So before even going to finite difference method, I want to tell you, why do we need discretization? So all the governing equations that we have, they are basically, as you say, a partial differential equation, and a PDE does not have an analytical solution. So the next step is basically to get an answer to these equations. The next best approximation that we have is we basically convert them into an algebraic equations, because we can easily solve algebraic equations. There are multiple numerical methods available out there which can solve algebraic equations. Some are really fast, some are really slow, but it's possible to solve the algebraic equations. And that is why we discretize. We want to convert these partial differential equations, which are the governing equations which govern the physics of a problem, into algebraic equations. So for example, on the top left over here, you see dou u by dou x. So this is a partial derivative, and an equivalent algebraic equation is right over here. It's basically u of I plus 1 minus u of I by delta x. It's just a simple difference that we see. And this is known as a forward type of partial differentiation, because we are considering u at I plus 1. The superscript n represents the time step. So right now I'll just you can ignore that term, I'll explain it later. And yeah, so the second one, as you see, it's called backward because we consider I minus 1. And the third one is central because we are evaluating this derivative at x equal to I, but the u's that we're using is at I plus 1 and I minus 1. And also, since I plus 1 and I minus 1 are basically 2 delta x apart, that is why the distances use 2 delta x and not delta x. And also, so for double derivatives, this is the equation over here. So you can easily derive this if you basically do go from first principles. It's not a tough derivation. And these are something which you should just know. I mean, know them at the top of your head. It's not really hard to by heart. And yeah, coming to the time derivatives. So we say a forward derivative when we, so basically now we are finding dou u by dou t at x equal to I, but we are considering two different time steps, n plus 1 and n. So n is your current time step and n plus 1 is your future time step or the next time step. So we say this forward when we are considering a future time steps. And whenever you do a forward discretization, there is a possibility that your numerical scheme, that your discretized scheme can be unstable. So there is a particular condition which makes it stable. So just the take home message is that forward discretization is not always the best way to discretize your governing equations. It's much more better to discretize it in a backward formulation because these are always stable. You will always have a solution. And if you basically discretize at a very small time step and a very small spatial step, you'll have a much more accurate solution. So always remember, if you have a choice either to use forward or backward, always go for backward. And yeah, so coming next is central, which is rarely used. Even the double derivative in time is rarely used. It's the backward. Most of the numerical schemes that you see, they used either first order backward or second order backward. So yeah, I wanted to just show a basic workflow for this finite difference method. So on the top, you see a governing equation. So this is just basically a 1D equation. It has two independent variables, the time t and the space x. So just remember the subscript over here means it's derived with respect to that particular independent parameter. So the next step in any CFD problem is to define a computational domain, and this is just a 1D problem. So therefore, you just have a single line over here, and I've discretized these into basically x equal to 1 to x equal to n. So we have n nodes over here. So first, as I said, we'll do a spatial discretization, and in spatial discretization, we used a forward discretization. That is basically the first one, the top one over here. And you use a forward discretization, and the next thing what I did was I discretized with respect to time. Now over here I am using a forward time discretization, the forward one, mainly because it's much more easier to solve right now. And another thing to notice is only this one's at n plus 1 and all the other time steps are at n. So this is known as an explicit time discretization. But on the other hand, even if the spatial discretization was at time step n plus 1, then that would have been implicit time discretization. So it's just basically explicit is at the current time step and implicit is when you use at the future time step. So that's the major difference. And as you know, now the unknown over here is ui of n plus 1. Basically the u at the next time step. We know everything at the current time step, and therefore this is on the left hand side and everything else is on the right hand side. So how this goes is, if you want to solve a particular equation, you will have initial values at time t equal to 0 already defined in the entire domain, and then you will plug in those initial values in these on the right hand side at all the i's, at basically all the spatial coordinates, and you'll find the ui at the next time step. And then basically this will keep on repeating until you get a converged solution. And by converged solution, I mean your ui at time at a current time step and ui and the next time step should have a very low error. So you see, whenever if you have used any CFD solver, you'll see a residual plot coming up. So you'll see the residual of 10 to the power minus 3, 10 to the power minus 5. So what those residuals mean, they are basically just error between the current time step and the next time step. So that is what you are seeing on that plot over there. So basically, in order to achieve an accurate solution, you need to have error less than 10 power minus 3 at least. And lesser the error, more accurate the solution. And yeah, so I wanted to also show another example. So this is an elliptical equation, as I explained before, and it's a double derivative over here. and that is why we discretize it like this. It's from the table, you can see it's the fourth entry from the top. So we use that particular discretization, and now over here the unknown is uij. So you put uij to one side and all the other terms to the other side, and again it's again an iterative process. So you have your initial solution already available and you're solving for uij. So you keep on plug-in, you insert your initial solution, find a solution for uij, and you do this for every particular point in your spatial discretization. And that is how you keep on iterating over different iterations, and you stop when the error between your current iteration and your next iteration is again very low, at least 10 power minus 3 or lower, which will be much more better. Now that was the basics of finite difference method, which is basically a good start to solving CFD problems. But all the softwares that you have heard of, let it be Ansys Fluent or let it be OpenFOAM or any other fluid flow software, uses finite volume method discretization and not finite difference method. So the main reason for that is finite volume method. You can, if you have any particular geometry, you can basically the right hand side geometry over here, you see it's a complicated geometry. It's literally impossible to solve it via finite difference method, or you'll have a very, very complicated code to solve that. So that is why finite volume method in this geometry performs much better. And also there's another problem with the finite difference method, is that one of the main governing equations is the mass conservation equation, which is not always conserved while using a finite difference method. But because of the math of finite volume method, it is always conserved. Finite volume method is developed in a way that mass conservation is a pre-existing condition into it. So yeah, so as you can see, these are complicated geometries which require kind of a complicated mesh, and for these mesh elements, it's always better to discretize your partial differential equations using finite volume method. And again, you get a set of linear algebraic equations from your governing equations, and there'll be one equation for each control volume. So you go if you have this particular discretization, you go over each cell and you discretize your governing equation on each cell, and for each cell you get a algebraic equation. And once you have those set of linear algebraic equations, there are multiple numerical methods. You'll have a matrix formation of the type Ax equal to B, where your x is your unknown, and you basically solve it iteratively. So one thing to remember before talking about finite volume method is that this particular theorem from calculus, which is known as the Gauss theorem. So over here, suppose phi that you can see here, if this is your main equation. So basically, for example, if you have a temperature governing equation or a heat governing equation, your temperature is the unknown. That is what you're solving for. So here phi represents temperature. If you have a momentum equation, then say velocity is what you're solving for, then phi is the velocity. So phi over here is the property that you're solving for. So, and if you take a divergence of phi, and this is a volume integral, so you're basically integrating it with respect to a volume of a cell. So if you take a divergence of that, this is also equivalent to phi times the ds, which is the surface area of the cell. So this is a very important theorem that we'll apply in discretizing the finite volume equations that I'll show on the next slide. And once you get this is still an integral, and to approximate it, we convert this into summation. So I'll explain what this means in the upcoming slides. So now you can see the governing equations that I have basically. And if you have any doubts, please stop me. I wouldn't mind answering your questions in the middle. I have no problem with that. Or basically, before going this, I would want to ask, does anyone have a doubt that they want to clarify?
You can put it in the chat box also if you are uncomfortable.
Sorry?
No, like if anyone has any doubts, they can put it on the chat box as well if they are uncomfortable switching on their mics.
Yeah, that also works.
Yeah, I had a doubt with regards to the finite difference method. We have something called upwinding, right?
Right.
What is that? Like, how is that different from backward or forward differences that we take?
So basically, upwind is a synonym for the backward type that you see over here. when you say upwind, upwind is basically upstream, or basically suppose you're solving for the node I, your I minus 1 becomes the upstream node and I plus 1 becomes the downstream node. So when you say upwind, it's basically using the I minus 1th node, which is just backward. It's just a fancy name for backward discretization.
All right. Okay, got it. Thank you.
Yeah. Anyone else? Okay, so I don't hear anyone asking doubts, so I'll just carry forward. Yeah, so we were at the finite volume method, and yeah, for this we have this particular governing equation that we'll be discretizing right now. And again, it's a very simple governing equation. It's just a 1D equation, and this is steady state. It doesn't even have a transient term. So we need to first deal with simple problems in order to understand how the finite volume method works in the background, and then we could go into more complicated problems. So again, the main thing is discretizing or seeing the computational domain. Now this is very important for finite volume method. So you have a 1D, just a 1D line over here, and at A you have a phi equal to A, one boundary condition given, and at B, say you have another boundary condition given, and you see these dots. These are the nodes at which you are solving the equation at. Now we are considering this particular dot over here, which is represented by P. So you see this gray shaded area, that is the control volume, or you can say the cell of node P. Similarly, E will have its own cell, W will have its own cell, and the bottom figure over here, it's just a magnified figure from W to E. So W is the leftmost point and E is the rightmost point, and again P is the center point, which is under consideration right now. So as you see, the P cell goes from the left hand side of the shaded area to right hand side, and we represent this particular face as small w and this particular face as small e. It's just basically to make the representation a little easier. So this is how we have divided the computational domain as of now. And now we'll first, and then on the next slide, I'll integrate these equations with respect to a control volume, and the control volume that we're seeing here is this shaded area. So it's a 2D, since now it's just it's a 1D problem. Sorry. Oh, did someone have any doubt? Okay, yeah, so since this is a 1D problem, our control volume is just basically similar to, it's basically delta x. So yeah, so now we basically, this is the equation from the previous slide, and I integrated with respect to dv. And now the next step over here is applying the Gauss divergence theorem, what I told you. So your divergence is nothing but d by dx. Divergence is basically a 3D notation, but since we only have 1D domain over here, this is the d by dx over here is equivalent to the divergence operator. So what the Gauss theorem said is divergence of any quantity is basically that quantity times the surface area. So it's basically this quantity over here, that is gamma d phi by dx times the surface area. So that is why that is what you see here, gamma d phi dx times this area over here, and gamma d phi dx times the area over here. Now what you see, these small e and w. So what's happening is, when we use the Gauss theorem, we have two different, we are basically converting the integral from a volume integral to surface integral, and this particular cell has basically one volume which is shaded and two surfaces, right? So there's w over here and e over here, so we have to consider both these surfaces. So that is why we have e minus w. So it's minus w because the outward normal for w is in the minus x direction, and outward normal for e is in the plus x direction. That is why we have e minus w. So basically what we did from this step to this step is converted the control volume integral into control surface, into area integral. That's it. And over here, sv into delta v, sv is just a source term, it's a constant which has come out, and dv just changes to delta v. So now we have this particular equation. Now we have this equation at the face e and face w, but all the values that we know of phi, of gamma, are at these at the nodes. We don't know the value of these things at these faces. So how do we calculate the value at faces? Is basically just to interpolate. That's the only way. So you have something at w, say gamma of w. The way to get it is basically you take average from this capital W and capital P. and that is exactly what's done over here. Basically, this gamma is at W, so we take the average of the two nearest nodes. Similarly, we do for E. So our E faces here, and if you take an average, it will be at the capital P and capital E. So that is what we have done, and yeah, so we plug it back in. Now another thing is also dphi by dx is at phase E over here. Again, we do not know anything at phase E, or whatever we know at the nodes P and nodes E. So we just use basically a forward difference formula. So at W we use Vp minus Vw, and at E we use Phi minus Vp, and basically the denominators are their particular distances, and we plug all of this in back into this equation to get this particular equation. Now this is an equation for one single node. So what the entire process that we did right now was just for this node P. We do this process again for W, again for E, and for all the nodes that are there in our computational domain. So therefore, the number of equations that we'll have is equal to the number of nodes that we have in a computational domain. So say we have 5 nodes in a computational domain, so we'll have 5 equations. If we have 10 nodes, we'll have 10 equations. So what's happening is we have a set of algebraic equations, and we have to solve these algebraic equations for the unknowns Vp, Vw, Ve. Again, phi is just a representation of a variable that you're trying to solve. This can very well be just a temperature. Phi can just be temperature if you're solving for the temperature plot. It can be any other quantity what you're solving for. I've just given a general notation over here. And that is what we do. So we solve this. So we get a set of algebraic equations, and we use multiple numerical methods and matrices to solve this. So this is what happens in the background if you have basically set up any fluent simulation anytime and you have hit run. What happens in background is something you never see. So this is essentially what happens in multiple 3D dimensions. Now doing this in 1D dimensions was a task. Doing it in 2D dimensions is also possible on paper, but doing it in 3D dimensions just increases the complexity a lot. And if you have a 3D geometry, you'll have multiple number of nodes, multiple number of cells. So therefore, it's not possible to do this on paper or by hand. So that is why we have these solvers present for us in order to simulate flow on a very complicated geometry. But as a CFD engineer, you should always code simple problems by your hand in different coding softwares. For example, in MATLAB or C++, whenever you get time, just take up any partial differential equation, discretize it as you get over here, and you get basically multiple algebraic equations. Now all you have to do is just use numerical methods in order to solve this, and see how your solution changes if you increase the number of nodes. If you increase the number of nodes, basically what you're doing is you're decreasing your delta x, because in the same length you have many nodes, so your basically spatial step size decreases. So this improves the solution by a lot. So yeah, so just wanted to give a brief introduction of what happens in the background, and if you have any doubts at this point, I can take it, because I'll be shifting to OpenFOAM with the next slide.
Pranay, in the case of finite volume method, we start off by integrating the differential equation, but we don't do so in finite difference method. Do we do so in FVM so that we can use the Gauss theorem?
Sorry, what was the last line? Could you repeat it?
In FVM, do we start off by integrating the differential equation so that we can use the Gauss theorem? Is that the only reason we start off?
No, that's not the motivation. So why we do this is basically what this process ensures is when you're integrating it, basically for a particular volume of a cell, it indirectly means your mass is being conserved in that cell. So there's a extensive math behind this thing, which I don't really have covered right now, but all it means is that when you integrate your partial differential equation over a particular volume, you're basically saying that your mass is always conserved in that volume, and that is why the finite volume method is better. Using Gauss theorem is just a way to convert it into algebraic equations, because you, at the end of the day, you cannot solve this partial differential equation.
Okay, cool.
Yeah.
Okay, I had a doubt. Okay, go ahead.
Yeah, Pranay. So my doubt was for, as you said, when we talk about 3 dimensions and stuff, the problem gets very complicated to solve analytically. So how do we when we come to the stage of validation for for fluid dynamics problems, how do we validate such 3D cases, the results that we get from a commercial software? How do we validate those?
So, for validation, there are different methods to do it. So, one of the best way to validate is if someone has done the experiments on the similar problem. So, for validation, you need a base solution that already exists. So, if you read any research papers, there are multiple validations done. So, the best ones is against an experiment that is done initially, or other cases. So, whenever people do CFD analysis, they use particular numerical schemes. So what I have shown you over here is just a simple numerical scheme in which, for example, you see dou phi by dou x. We just use this particular simple approximation, but this, to be honest, is not really accurate. It might work well for such a simple problem. For a more complicated problem, approximating this differential just as a finite difference approximation over here will not really work well. So we have different schemes to approximate this dou phi by dou x, more accurate schemes. So what people do is people use these different schemes to finally formulate the algebraic equations, and they validate one scheme versus the other. So validation is all about having an initial solution which you can trust, and then that solution can be anything. It can either be a prior CFD analysis done by someone else, or it can be an experiment already existing.
All right, thanks.
Yeah.
Yeah, so I wanted to know, like, in case of a 3D, we have like a lot of faces, and like, how does the software account for all the faces, no matter how much unstructured the grid is? Like, how does that happen? Like, we go for very arbitrary grids as well. So when we apply this, yeah.
So basically, just for okay, so over here we have two faces, right? For each particular node, it's the W face and the east face. And the way we accounted was we are basically summing it up, and we are applying appropriate signature based on the surface normal. So suppose you have, say, a 3D mesh in which the cell has, say, 8 faces. So you'll have 8 such terms. Basically, it's just that. So basically, it's not really hard to convert a 3D this thing into 8 different terms. You have to just ensure that you have given it appropriate signs. That's it. So it's just that it's more complex to solve it by hand. It's not like it's impossible. You can very well do it, but it will be very, very cumbersome to do so.
Yeah, okay, thank you.
All right. So I'll start with the final part of this presentation, which is OpenFOAM. So OpenFOAM is, the full form stands for Open Field of Operation and Manipulation. So it's a free software, meaning you can just go to OpenFOAM's webpage and download it, and you can just start using it. But you need a Linux system for it. It cannot work on Windows, or lately it's been working on Windows, but there's a work around it. I have always used it on a Linux system, and so it's completely free. So it's you can get it at no cost, and OpenFOAM has a lot of numerical schemes available, and basically it's on the finite volume method which I just described, and it has a continuum mechanics. So basically when we go to very small lens lesser than micrometer dimensions, for example microfluidics, we cannot assume continuum mechanics. We have to consider the mean free path of each of the fluid molecule, etc. Such a system cannot be simulated in OpenFOAM. So it has to be, your continuum mechanics assumption should hold when you're using OpenFOAM. And in OpenFOAM is basically written in a C++ programming language. So it's very essential to know C++ if you're using OpenFOAM. So just as a comparison, so OpenFOAM, as I said, is free of cost, which other commercial softwares are not. And parallel computing is possible in both OpenFOAM and in commercial softwares. So your source code is the code. For example, it's the code in the background which is running. So there is all the source code here is the governing equation which has been discretized. So that is running in the background. So now if you have simulated an Ansys fluent problem, you honestly can't tweak the governing equations. For example, you want to say add a body force to it or any other force, you can't do it manually with your you can't add it to the equations, but that is possible in OpenFOAM. You can go to a particular file, manually add another term, and then your governing equations will take care of the impact of that term in your solution. And again, you can redistribute your code. So if you have multiple people working on OpenFOAM, that's always a good idea. And finally, the worst part about OpenFOAM is the documentation. So the basically it's a very it's the if you're learning OpenFOAM initially, the learning curve is pretty steep. So but there is not a lot of documentation. So if you're using Ansys Fluent, there is an entire manual guide explaining what each button does in the what's actually happening when you press that button. But that is not possible with OpenFOAM. And another thing is OpenFOAM is on a Linux environment, so you don't have buttons. In Ansys Fluent, you have a proper GUI. You click on boundary conditions, another tab opens up. That is not there in OpenFOAM. In OpenFOAM, you must know how to navigate through your Linux page. So so just to show you the compatibility, so there in OpenFOAM, when you first download it, there are a lot of inbuilt solvers already present. You just have to go there, make your mesh and hit run, and you get a solution for that particular problem. So basically, for example, the most basic one is a Laplace equation, which we just saw previously using finite difference method. And if you have an incompressible or compressible flow, there are different solvers. So I'm pretty sure there are more than 50 solvers already available. And if you have multi-phase flow, there's Euler. There are different multi-phase solvers already available for turbulent flows, for diesel flows, and also there is a small subset which is used to investigate the solid mechanics as well. So in me personally, I have used a solver regarding the Euler solver. So basically what people do is people just don't use OpenFOAM solvers. These solvers are already existing. A user just has to come and play hit, and basically these solvers are there for a particular geometry, for a particular physics problem. So these are all the basic physics problems. If you're doing analysis, your problem might be much more complex than the basic physics problem for which the solver is built. So what you do is you take this basic solver, you make a copy of it, and then you change all these settings of these basic solvers, which will reflect the settings of your custom problem. So for example, in my research here at Purdue, it's regarding multi-phase flows, but at very low Reynolds number. But so I take up a Euler solver and I made a copy of it, and then I went into the governing equations. I added or I subtracted some of the terms which are not relevant to my particular problem, and then I'm solving this equation. So this is why OpenFOAM is really helpful. If you know your fluid mechanics well, if you know your governing equations well, and if you know C++, you can do anything. You can basically tweak the equations, add more terms, remove some terms, and that is why it's much more stronger, because it's open. There's nothing hidden from the user. But on the other hand, in Fluent, you really don't know how it's solving your problem in the background. You cannot see anything. You cannot tweak your governing equations. Navier-Stokes will be solved. You cannot say take out all the terms on the left hand side of the equations, which I can do if I'm using OpenFOAM. So just introduction, this is how easy it is to tweak a governing equation. So this is a general governing equation for turbulent kinetic energy. So if you're solving a turbulent flow, you'll be solving for this parameter K. And in the background, this equation is coded something like this. So ddt is basically because of derivative with respect to time, and the bracket is K. And here the second term is divergence of phi. So U is basically nothing but phi over here, because we are solving for in OpenFOAM the terminology can be a little confusing. U means phi, so divergence and phi and K over here, because there are two terms inside. And this is the Laplacian term, because there's divergence and there's another divergence inside. So this is the third term. And over here is basically the right hand side of the equation. So this is the grad term over here. And finally This is epsilon by k times k. So all these things that you see fvm is basically because these terms are the unknowns. They go on the left hand side of the so whenever you're solving a governing equation, you discretize, you always get it of the form ax equal to b. So whatever term go in this A matrix, that is related by m, and whatever the term that you know goes into the B matrix. So I'm not, my intention is not to show you what ax equal to b is, but my intention is to show you that how easily it is to code these equations, and this is already coded. So now if I want to solve a steady state analysis, I'll just go to the source code and remove this term. I'll just delete it. That's it. That's about it, and I'm getting a steady state equation, steady state solver. So yeah, so about pre-processing. So OpenFOAM is it's based on finite volumes, and you can have any mesh. You can have an unstructured or a structured mesh. It can be tetrahedral, hexahedral, or mixed, or anything. And two of the main commands that is used to build your mesh, that is to mesh the domain that you have, they are known as block mesh and snappy hex mesh. So now these commands are case sensitive, so you must type the M capital. You cannot really type it small. Otherwise it will shoot out an error saying block mesh with an M small is like error, the command not found, something like that. So basically this is the command you type in your terminal's block mesh, and your mesh will basically come in your domain. And snappy hex mesh is more of a complex command. And also another thing is OpenFOAM meshing is not really if you have a very complicated geometry, people usually prefer using more complicated meshes, for example Gambit or star CD, etc., or even fluent meshing, and then you can import that mesh into OpenFOAM. So in OpenFOAM all you're doing is just doing the analysis, you're meshing it in some third-party software. So in such a case, OpenFOAM has these commands known as fluent mesh to foam or gambit to foam, which converts these mesh into OpenFOAM meshes. So it's just basically when you type these commands, it's just writing a mesh file. It's just translating the mesh file. That's it. So basically, they had to develop these commands so that if the user wants to have a choice of meshing it somewhere else and just solving it in OpenFOAM, it should be possible. So that is what these commands end up doing. And so now I told you on this slide that there are multiple solvers. So in each, suppose we are using this solver, Laplace solver. So basically when you enter the solver, there will be 3 different files. Those files are 0, constant, and system. Each file has another separate files within them. So what 0 file has is, it will contain the variables that you're solving for. So basically now a CFD problem has to have boundary conditions and initial conditions defined within them. So that is what you do in these folders. In velocity, you will at different walls of your computational domain, you will specify the velocity and the pressure. And the constant folder has all the constant properties. So now, of course, if you have a viscous flow, you'll have a viscosity term. So you need to define that viscosity value somewhere. So that is what you do in this constant folder. And also all your mesh, basically number of edges, number of points, etc., all that information is stored here. So this is not a use to the user. It's mainly this transport properties file in which you define all your constants. And finally, the system folder. So system folder has 3 different subfolders. So this system folder is where your CFD modeling comes into picture. So you have to define your time step. What is your time step, number of time steps, how long you want the simulation to run, and what are the different discretization schemes. So we just saw some of them, for example, forward, backward, etc. So which scheme you want to use for your solver. And finite volume solution is basically so now you have your linear algebraic set of equations, you have to solve them somehow. So what particular numerical method will you use? Will you use Runge-Kutta, or will you use any other numerical method that you know? So all these settings has to be done. So whenever you open OpenFOAM and you navigate to a particular solver, that solver will have these 3 files, and each of these 3 files will have these subfiles always present within them. Once you're done setting all of these, you will go ahead and type block mesh. That will basically generate your mesh, and then you'll go ahead and again press run. That will run your solution. And I just wanted to basically show you what.
Hello.
Yeah.
What
Hello.
is grid independent study?
So basically if you have a computational domain, how do you know what's the optimum number of grids that you have? You can have a very coarse mesh, so that will basically not capture all your physics, or you can have a very very fine mesh that will of course capture all your physics, but it will take a lot of time to run. So therefore there is an optimum number of mesh count present. So in grid independent study, what you do is you basically whatever parameter is of your interest, for example temperature, you see how the temperature changes with different particular number of meshes. So for your value will change drastically for very low mesh to a very high mesh. So grid independent study is basically to find a mesh count after which your temperature value does not change. So what that means is you have found your optimum mesh count. If you go higher than that, it just increases your computational time, but this does not improve the accuracy of your solution. I hope that's clear.
Yeah, got it. Thanks.
Yeah. So here just some of the examples of the different solvers that I could find online. I'm pretty sure there are a lot more than them, and these solvers are just, so you see some of these are just for incompressible flows, but for different scenarios. So suppose you want to solve today for incompressible lamina and a Newtonian fluid, you'll go to ICOFOAM. But if you want to do the same thing for non-Newtonian fluid, you'll go to non-Newtonian ICOFOAM. So based on each of the specification, there might be additional files, but these 3 basic files what I showed you will always be present in all the solvers. But there might be additional files present because if you are specifying non-Newtonian fluid, you might have to specify the non-Newtonian property somewhere. So that is what, there might be additional files. So OpenFOAM is more about, if you're using a particular solver, you go online, look up everything about it, how it's done. There are a lot of tutorials present for each particular solver, and then you try to replicate that in your own model. So it's basically a lot of googling involved. It's not as easy as Fluent, because in Fluent you just have to make sure you click each button and you make sure you have the correct specification for your particular problem. But in OpenFOAM you have to navigate back and forth, Google online and do a lot of research. But it's a little uncomfortable in the beginning because it's very overwhelming. But once you know how to navigate through OpenFOAM and what different folders contain, it becomes much more easier. It's much more powerful because everything that you want, you can tweak in the background and see the results for yourself. So yeah, that's about it. Thank you for your attention, and if you have any more questions about the presentation or anything else, please let me know.